So our next speaker will be Anvar Shukurov from Newcastle University. And the title of his talk is Magnetic Fields and the Multi-Phase ISM.
Excellent. Thank you. Excellent. Very technically advanced. Excellent. So, when I first learned about this meeting, I immediately knew that I should and I will come for just to pay my respect to people from whom I learned so much. When I started my PhD, it was the first time that I was exposed to astrophysical magnetic fields, and at that time I was learning how to combine physics and mathematics in the group of Zeldovich in Moscow, and I was left to myself to learn how to combine physics and astronomy. And then, very, very soon, I started distinguishing from the stream of published papers, which was by far thinner at that time than now, the papers of Crutcher, Heiles, and Roland, from which I learned a lot. I learned how to combine physics with astronomy to get what you call astrophysics, and also this exquisite logics and clarity of both their thinking and their writing. So, thank you. I owe a lot to you well before you knew about that and even heard about me. This is why it was totally impossible for me not to come to this meeting, and thank you very much for having me. So, the results I want to present are very much work in progress, made in our group in Newcastle, and there will be another talk tomorrow of James Hollins, who is here, which will also sort of analyze the systems I will be discussing today. I will first introduce the numerical simulations we use as our main tool, and then I will focus on magnetic effects on the multiphase ISM, trying to isolate those which are more unexpected and counterintuitive, at least to us. And then, I will have no time to discuss in what phases of the stellar medium the magnetic field resides, where is the home of the large-scale magnetic field and small-scale magnetic field, in the warm gas, in the hot gas, in both. I will not have time for that, but I do hope that I will have time to discuss the need for new analysis methods to compare complex models with complex observations. A new level of complexity in both modeling and observations requires new tools. And what are those tools? I hope I will have time for that. So, I will introduce the simulations I will be using. It's the simulations of the interstellar medium driven by supernova explosions, and they're fully three-dimensional, non-ideal, all diffusivities, magnetic diffusivities, thermal diffusivities, viscosities are included, fully nonlinear, compressible, include magnetic field, include heat and kinetic energy sources from supernova explosions, radiative cooling, optically thin radiative cooling. We have rotational velocity shear and external gravity. There is now quite a range of models which contain similar list of physical factors, but this model and the other one of Gressel and Detlef Estner, only those two models admit healthy dynamo action and therefore admit physically realistic magnetic fields. These are the equations we are solving. If you're interested, this is their form. Nothing complicated, they're just more or less standard. And here, this is how our box looks. Now, this is the gas density in the box. This is gas temperature in the box. This magnetic field in the box. We start with negligibly weak magnetic field. Everything is black. White means 1 microgauss. The range of densities is from 10 to the minus 4 to 100 particles per cubic centimeter. Range of temperatures that we can capture is about from 10 Kelvin to 10 to the 8th 100 million kelvins. The box size is 1 kiloparsec by 1 kiloparsec horizontally and 2 kiloparsecs vertically, and we put here external gravity to mimic the gravity near the solar orbit. So the midplane is here in the middle of the box. Our resolution is 4 parsecs, and it's controlled not by the size of our computer, not by the amount of money or time we have, but we have shown that with this resolution, it's a minimum resolution, which allows us to reproduce the known analytical solutions for the expansion of supernovae from the Serov-Taylor phase out to the 100 parsecs diameter when they merge with the interstellar medium. We reproduce with this resolution those analytical and numerical results within 10%. So these are physically chosen resolution. Mach numbers within the box can be up to 25, so it's quite a demanding simulation. Do you remember this box? It was black, right? And look how violent is this medium. Roughly, this is our galaxy near the sun in its own real time. This way we live. What we observe with our telescopes are just snapshots, right? Which can look ordered and non-random. But in fact, in the real galaxy's real time, this way we live. It's enormously violent, enormously random medium. And what is surprising is that magnetic field is half a giga-year in physical time. It grows magnetic field. And what is amazing is that this field, which is in this box, contains both the random component and the mean component, which is non-zero across the box, horizontal field. So here we have, in this violent medium, we still have the dynamo action, both at small scales and the large scales. The mean magnetic field grows from negligible amount to 1 microgauss within the box. This is how the thermal energy behaves. Each little peak here is one supernova explosion. Kinetic energy is in the steady state, when then part of it is consumed by magnetic field. Magnetic energy grows almost exponentially. It's a dynamo action, exponential growth, not linear in time, exponential growth, and then saturates. The saturation time is about 1 giga-year, which is the time where magnetic energy becomes comparable to the kinetic energy of the random flow, The correlation analysis of this horribly random medium will be presented by James Hollins tomorrow, and the results are by far better than you might expect from those movies. You will see. I hope James will impress you. So, what magnetic effects? This again is work in progress. There is an obvious, known to everybody, magnetic effect on the multiphase ISM. Contributes to total pressure, perhaps under certain conditions. It can make the disk thicker. I will not talk on this. There is another important thing for which I have no time, that cosmic ray diffusion in these sort of magnetic fields can be entirely different from the Gaussian random magnetic fields usually assumed in cosmic ray propagation. I will concentrate on the effects on the multiphase structure of magnetic field. So this is the probability distribution function, two-dimensional PDF, or in the temperature density plane. Temperature is here, density is here, and this is the number of pixels with given temperature and given density. PDF. You normalize it, you get PDF. Magnetic field here is 0. First hydrodynamic run. Here we have a healthy three-phase medium. This is the warm gas, one peak in the probability. Hot gas, another peak at 1,000,000 degrees, 10 to the 4th kelvins. And then this is the cold gas. So and these lines are the lines of constant cooling time. Constant cooling time. Now, what magnetic field will do with this? This is basically the same probability distribution, but now just with different color scheme. the same stuff. And this is now with magnetic field. With magnetic field. First, what happened was that this tail has become narrower. It became by far shorter. The distribution is by order of magnitude narrower. Here the range is 10 to the 8th, 10 to the 2nd. Here, less than that and less than that. So what magnetic field has done with my interstellar medium, well, I will use a word borrowed from dairy industry. Probably in Wisconsin it's appropriate, right? It's the homogenization of the interstellar medium by magnetic field. Why? What happens? How magnetic field can reduce the amount of cold gas and, even more surprisingly, reduce the amount of hot gas. With cold gas, it's okay, it's understandable. Magnetic pressure just prevents compression at small scales, and therefore it's perhaps not surprising that there is a less of cold and dense gas. But why hot gas? What happens with the hot gas? Here, these are volume filling factors within our box, fractional volumes, of gas in different temperature ranges. So, with this time in gigayears, 1 gigayear is here. So first, the hottest gas, red curve, fluctuates. This amount of these fluctuations is large. This is the measure of how small is our box. Obviously, you would like to have a box much far bigger to avoid such strong fluctuations. But of course, it's better to be rich and healthy, but sometimes we have to choose. In this case, we have to choose a smaller box for the benefit of having rich physics. So it is of the order of perhaps, well, 10 or 20%, but then it decreases after about 1 gigayear down to smaller values. Meanwhile, the slightly cooler gas, its volume filling function increases. Likewise, the coolest gas, this gray line, again, the amount of gray gas, of cool gas decreases, and the warm increases. So the range of temperatures becomes narrower. The range of densities becomes narrower. Why? And this happens exactly when magnetic field becomes, in kinetic energy, becomes comparable to magnetic energy. Why? What happens? To understand, this is the picture. This is the slice through our box without magnetic field, and this with. This is the certification is in place, hot gas is in place, but everything is by far more homogeneous. Why? What happens? Well, obvious suspect is magnetic tension. Here is the magnetic vertical velocity. Well, hot gas drives the outflow. What happens with the outflow? This is the outflow at z larger than 0, z less than 0, multiplied by -1, obviously, for negative z. Again, it's of the order of, it's average of the whole box. So about 10 kilometers per second, and then it decreases virtually to 0. When does it start decreasing? Exactly where magnetic field becomes strong. So magnetic field not only homogenizes the medium, it also suppresses the outflow, suppresses what we believe is the base of the galactic fountain. Why? And this is the result also, the recent paper of the other group, which have dynamo action, and they also have similar dependence. The outflow velocity is suppressed by magnetic field. Beta is the ratio of magnetic field to kinetic energy density. Drops as magnetic field becomes strong. Why? This is the magnetic tension as a function of time. Of course it grows because magnetic field grows, and then there is slight dominance of the red curve, which is the vertical component of the pressure, or of the tension. I think it's magnetic tension, it's normalized. So I divided now the magnetic tension by RMS value, and it's decreasing. Decrease means that it's a result of restructuring magnetic field. Large scale magnetic field grows, therefore the scale increases and the potential decreases. And this morning I made this simple estimate whether this magnetic tension will be sufficient to stop gas, to stop the outflow. Yes? it seems that up to 100 kilometers per second can be stopped over one crossing time with this sort of magnetic tension. So these are my conclusions. First, magnetic field makes interstellar medium more homogeneous than it would be without magnetic fields, and globally, not even locally, and weaker galactic fountains and winds from magnetized galactic disks. And this is what I didn't have time for, maybe just a few words. What we have, and we saw it in this movie, we have a statistically non-uniform, stratified random medium. It's very far from being Gaussian. It's extremely intermittent, with lots of small-scale structures where the random phase approximation doesn't apply at all. So, power spectra, 2, 3, 4, 5, 7, 25 point correlation functions are of very limited significance. What's then? What tools we have to study such random fields? There are some, and for me, the most promising is what is
Anvar, I think we got to wind up.
Topology. Sorry?
We got to wind up.
You can read it yourself. Thank you.
Yeah. I don't think we have. So one question, Chris.
Yes, I was wondering why it took so long for the magnetic field to get amplified, since you have turbulent motions on small scales that can amplify the field very quickly. And in cosmological simulations, for example, people have shown that even in the intergalactic medium, the field gets amplified up much more rapidly than in a gig year.
Well, the time scale, the exponentiation time scale is 130 megayears. It's an Edison-over time. But we start with a very weak field because I want I want to genuinely see how it's generated and to see the effect of the growing magnetic field on my medium. I want to know what magnetic field does with it. Therefore, we start with negligible magnetic field. It was unfolding every 100 million years until
my question was, why is that so long?
Why? It is Edison over time.
But the
10 kilometers per second, 100
turbulence on
parsecs.
small scales, which is much faster.
At very small scales, yeah. But at energy range scale, at 100 parsecs or 50 parsecs, it's 100 million years.
Thank you.
Thank you.